Good afternoon, my YouTube viewers. It is Crystal here. I'm just here because I want to do a code review on Kaggle's Playground series, Season 3, Episode 10, which is going to be about pulsars. And I used Keras Tensorflow on this because I'm studying Keras Tensorflow. So I'm trying to move away from sklearn and into TensorFlow because I read somewhere that TensorFlow is actually more popular than sklearn. I don't know if that's true, but sklearn is definitely easier to use than TensorFlow, so I'm definitely going to have a big learning curve. So this playground series competition is about pulsars, and I got 0.06, which was about the middle of the road. And there were some things that I could have done to try to improve my score, such as employ feature selection, which I didn't. I just used all of the features. And two, like maybe train the model through more epochs, which I only put it through 10 epochs, and it took me an hour to do 10 epochs, so it averaged 6 minutes per epoch. And since I don't have a lot of time, I just left it at 10. So those are two things that I could have done to improve the score, but I decided not to do that because I'm busy doing other things. I'm studying TensorFlow, and I'm also creating content. And if I had two computers, if I had broadband and an extra computer, then I could train it and save it on one computer and then work on another. But I don't have an extra computer. My broadband is not strong enough. I just get internet from my phone. So I'm just telling you now that if you want to use my code and you want to try to improve your score, then those are some things that you can do. Either exercise feature selection or increase the epochs or increase the iteration. So we've already talked about what happened when I submitted my work to Kaggle. So now what we'll do is we'll do the problem statement. Is the data set for this competition, both train and test, was generated from a deep learning model trained on the pulsar classification. Feature distributions are close to, but not exactly the same as the original. Feel free to use the original dataset as part of this competition, both to explore differences as well as see whether incorporating the original and training improves model performance. So I will say that I did do some visualization, but it was in the middle of the night when I worked on this, so I didn't do lots of visualization of the features, but I did do visualization of the labels, and I made a heat map. But, obviously I could have done more visualization of the features. So what we're going to do is we're going to create the program, and we created the program in Kaggle's free online Jupyter notebook. So that was good. So I didn't have to use my memory space. I can use Kaggle's memory space. And then what we want to do is we want to import the libraries that we're going to use. So we're going to import NumPy as NP for numerical computations, import pandas as PD for data processing, import OS to go into the operating system, import matplotlib pyplot as PLT for visualization, and import Seaborn as SNS. We're also going to import in the program sklearn for machine learning functions and Keras Tensorflow for the neural networks. So that's what the libraries that we're going to be importing. So after we've imported all of our libraries, we're going to load the files using OS, and then the 3 files that are in this competition are train, test, and sample submission. So we're going to use pandas to actually read the files and convert them to data frames. So it's going to be train, test, and submission. So you can see train, they've got 117,564 rows by 10 columns. And then you've got your class. And there's a lot of zeros there as well. You've got your train info. There's all integer and floats columns. So that's good, so we don't have anything to encode. So you've got your mean integrated SD, EK, skewness, mean, DMS, and R curve, SD, DMS, and R curve, EK, DMS, and R curve, skewness, DMS, and R curve, and then your class. So the train shape is 117564 by 10 columns. The train size is 1175,640, and that's your cells. And we've got train describe, and so this gives you the basic statistics of the data set. I did the value counts to find how many zeros and how many ones there were. So you can see that we've got lots of zeros and not very many ones. And I created a histogram, his plot of that. And you can see we've got a class imbalance where you have a lot of zeros and not very many ones. So that's a class imbalance. And then we check the test file. The test file is the same format as the train file, except for the fact that it doesn't have a class, because that's what we're going to predict on. Check for null values. We don't have any null values, so we don't have anything to impute. Then we check the submission. So with the submission, the class is going to be a floating number. So I was just assuming, as you do, that they were going to want the probability. So instead of wanting a 0 or a 1, they wanted the probability, and that's just what I was assuming. So now what we're going to do is we're going to define our target. So target equals train class. And we're going to combine our train and our test, and we're going to create a variable combi, which is going to hold the train where you've dropped the class and appended the test. And then we're also going to drop the ID, and you don't need the ID. The reason why you don't need the ID is because all of the examples are indexed anyway. I created a heat map. So core equals combi.core, SNS heat map core. So you can see here that the a lot of the columns are highly correlated. So if I had wanted to, I could have removed some of the columns, but I just decided not to. I just decided to leave all the columns as they were. Here's the data. Here's the code where you can remove the columns, and I just put 0.99 in there so it wouldn't remove any columns. But you could say 90 or 95. 90, I think you would remove a few columns, and 95 you would remove less. But I just thought about it, and I thought, well, I'll just go ahead and keep all the columns in there, even though they have a high correlation. And then we're going to normalize the combi. And when you normalize the combi, you take all of the cells and you convert them to a value between 0 and 1. And the reason why that is because it's easier for the model to predict on the data if it's closely dimensioned. So now what we're going to do is we're going to define our X and our Y variables, and they're your independent and dependent variables respectively. So your Y is your target, Your X is combi, row 0 to the length of train. Your X test is combi, length of train to the end. And then we're going to check the shape as well, so you can see the shape, because that's important to make sure that the shape of X and Y is similar. Now what I've done is I've defined a variable called num feature, which is the length of X columns, and we print the num feature, and that's 8. So that's telling me that there are 8 columns. And now we're going to use sklearn to split the data set up into training and validating sets. And when we've done that, we're also going to check the shape as well. So it's very important to check the shape. So now we're going to select our model, and we're going to use Keras Tensorflow. So import TensorFlow STF from TensorFlow import Keras, print TensorFlow version, which we're on version 2.11. So this is the model that we have built. Model equals Keras.sequential, Keras.layers flatten, input shape equals num feature, comma, brackets, Keras.layers dense 128, activation equals tf.nn.relu, Keras.layers dense 256, activation equals tf.nn.relu, Keras layers dense 256, activation equals tf.nn.relu, and Keras.layers dense 1. That's your output. Activation equals tf.nn.sigmoid. So that's telling you that it's a binary classification because it's sigmoid. And now what we do is we compile the data into the model. So your optimizer is going to be atom, your loss is going to be binary cross entropy, and your metrics is going to be accuracy. And then we do a model summary, so you can see the model summary here. And now we fit the data into the model. I set it up for 10 epochs. It took me an hour just to go through 10 epochs. And batch size equals 1. So I suppose we could have had a bigger batch size. We could have put a batch, because it says batch size equals 1. We could have had a bigger batch size. We could have said, like, maybe batch size equals 64, and see what happens with that. So test loss, test accuracy equals model.eval, xval, yval. So I might try that batch size. I might ask the question. Let's see. Using a batch size of 64 achieves a test accuracy of 98%, while using a batch size of 1024 only achieves a batch size of 96%. By increasing the learning rate using a batch size. So, let's check another one. Our results concluded that a higher batch size does not usually achieve higher accuracy. But it definitely would improve the speed if you have a higher batch size. And the learning rate and optimizer use will have a significant impact as well, lowering the learning rate and increasing